So today we'll continue from where we left off in the previous session on statistics. So we'll do a quick recap and we'll take a little further in today's session. So as in the last session, we've looked at few basic fundamental statistical topics. We looked at data distributions, right? Particularly normal distribution, perfect normal distribution, and then we also saw a couple of what a skewed distribution will look like, right skewed, left skewed, and we have also understood the concept of outliers and how do we normally eyeball them given a data distribution, and we also saw how the measures of a center, right? So given a data distribution, how do we identify what are the various measures of centers that we can use to distinguish these distributions. So we have seen mean, median, mode. We have also understood where to use which one, and we saw that median is more robust measure of center than mean when there are outliers involved in your data. So this is the broad summary points that we looked at in the previous session. Today we'll continue to look at measures of variability. So these involve some of the metrics that you are familiar with, something like variance or standard deviation, something like this. We'll go through this. We'll first understand, we'll try and get the sense of what variability in distributions are and why the variability is important. We'll take a couple of examples. We'll get a sense of why variability is important and in what type of statistical questions do we normally use, or we bring in the variability concept to answer those questions. So yeah, so today's session is broadly about that. Let's get started. So okay, so if we see here, we have a bunch of normal distributions in the chart on the slide as of now, and all of them, or the different colors that you see, are basically all of them are normal distributions. And one other, if you can notice, one thing that is common for each of those different normal distributions is that all of them have same center. So be it since all of them are perfect normal distributions, for any distribution it will coincide that mean equal to median equal to mode, and at the moment that mean and all those three measures of center are equal for all of those different data distributions that you see. But even then, the measure of center is same, but we can see that there are different distributions, and that is because from the point of view of variability. So if we see the range of each of those distributions on the x-axis, so we can see that the purple line, which has the lowest range we can assume, and then as we go to a red line, it has a slightly higher range on x-axis when compared to the purple one, and green a little higher, and then this black a little higher, and yellow, and likewise, right? So what distinguishes obviously these data distributions here in this slide is normally the variability factor, not the measures of center. So for example, as I said, standard deviation is one of the popularly used measure of variance. We will see how it's calculated and then how is it related to other measures of variations. But for the time being, if we have to get the standard deviations of each of these curves, we can see that the one with the lesser range, the blue color, has the lowest of all the standard deviation measure of variance, 0.75, and as we go across, red one has slightly higher 1.25, 1.5, and the one with the higher range, which is this black line that is going across this 0.2 line, we can see that it has a standard deviation of 2. So as the we'll see that, and we'll see how it's calculated and all. But just to, from this assumption, from this pattern that we see here, right? So as the curve, the distribution changes the shape from more of a peak kind of a thing to a more of a flat sort of a distribution, we can see that the standard deviation is increasing. So with the same pattern, we can come to a conclusion that if the data distribution is more flat, right, almost parallel to the x-axis, then the standard deviation for that distribution would be something that is close to infinite. Okay, so this is how normally in the data distributions, how for the data distributions which have the same center of measure of center, the measure of variance can be used to distinguish among those sort of distributions. Now let's understand why variability is important, and in what kind of questions does this variability can be used to used for in statistics. Okay, let's for that, let's try and take a specific example before to understand. Okay, okay, so I have a normal distribution on the right, and let's try and relate that to a particular example that which we are already discussed in the past. Okay, let's say you're trying to procure milk to supply to a residents of a city, right? And you have conducted a survey, and you find out that what is the to understand like how much should you start procuring each day, and how, so that you will understand how much you should supply on each day. So obviously the first thing you will target is you will get a data distribution of all the of the data that you've collected through a survey. You'll see how many families are consuming, let's say, how many liters of milk. So on the x-axis we have the quantity, how many liters of milk, and on the y-axis we can say it as number of families. Okay, so we have around like 4 families that consume 1 liter of milk per day, and likewise. And from the normal distribution, I can say that something around 10 or 9 would be our mean. So that would be the average consumption per family per day, 10 liters. Let's just think of it as imaginary data. No family, I think, will consume 10 liters of data, 10 liters of milk. Okay, but mean is something around 10 liters. So you can say that, hey, okay, the mean is coming around 10. So I can, if I have some 1,000 families that I need to cater to in the residents who are willing to take my product or purchase my product, then I would say 10 into 1,000, 10,000 liters of milk is what I should target to supply on a day-to-day basis. Now that is the analysis that you can, that's the question that you can answer using the mean, right? Just the mean. But let's try and see the question where the variability or the one that we just saw, standard deviation, is used to answer the question. In the same example, let's say there is a situation, a hypothetical situation, where the milk is in severe shortage. Okay, you're not finding, there is a huge demand, and but the supply is in very severe shortage. Now you need to understand, you have to answer, let's say, some sort of a question like, you need to put a upper threshold on how much a family can consume per day. Okay, so it should not exceed that. So let's assume that, and you need to know what I should set, how much should I set the upper limit, so that 80% of all my customers are met with their daily requirement. So that is the question that we can think of answering. So there is a severe shortage of milk. I cannot just allow customers to purchase however many liters that they want. I need to set a limit, and I should only allow them to purchase below that limit. But I can, there is a chance that I can see that here, if I set the limit as 1, okay, 1 liter, there is only like a few, 4 plus, let's say, 1. There will only be 5 families of all the families that I'll be that will be met with the requirement. The rest of all these families will not be, though they might get 1 liter every day, but that will not meet their requirements. So I should make sure, hey, at least to ensure that most of my customers are happy, let's say the business has come up with this sort of a solution, hey, and let's try and keep the upper threshold in such a way that 80% of my customers meet what they require on a day-to-day basis. Now, in order to answer this question, we need to bring in a standard deviation and a variance analysis. We'll come to that. Let's see how it can be done. The same normal distribution that we just saw earlier can be also represented as in this format. Okay, let's go one by one. If you just focus on the shaded region here, we can see that we can notice a couple of things. One, the shaded region is split into few horizontal segments with the lines, and each of those horizontal segments is given a certain percentage. This percentage is nothing but, hey, in this particular horizontal segment there are 19.1% of customers, and since this is a symmetric perfect normal distribution, the percentages will be symmetric across the center, so 19.9 on both sides of the center, and similarly the second segment from the center will be 15% and 15%, and likewise. Now, how these percentages are arrived at, we will come to that later, but this is how, given any take any normal distribution, if it's a perfect normal distribution, will definitely have these percentages as it is. There will not be any change in the percentages. So if it is slightly deviating from a perfect normal distribution property, there might be slight changes in the percentages, but approximately it'll apply same percentages. Okay, so now let's just read the data which is below the chart. Ignore the z-score for the time being. We'll come to that in the right time, and we can focus on standard deviation. So there is something called standard deviation. We will see how it's calculated and all, but let's see how the standard deviation is being used to answer this question at the moment. Okay, so we can see that I have a center 0, so my standard deviation value is 0 at the center. Okay, and as I progress across each of these strides, my standard deviation is increasing. So here it's 0.5 standard deviation, here is 1 standard deviation, 1.5 standard deviation, 2 standard deviations, and etc. And likewise on the negative axis we have a similar scale. Now, as you can see here, below that, the standard deviation, I have a cumulative percentages. What it's trying to say is, always remember that on the x-axis, though we are showing z-score, standard deviation, and all these values here, but what our x-axis represents is that the number of liters of milk, as we saw in the previous. These same values will continue in here as well. So if we say that, for example, here let's take an example of 2 liters, right? So if I set the 2 liters as my threshold, then it's saying that cumulative percentage, hey, up until that 3 liters of milk, I have only 0.1% of the entire families. So I'll only be able to meet the requirement for 0.1%. So as I progress, let's say maybe up until here, if whatever the value that I take here on the x-axis and I put that as a limit, I'll see what is the cumulative percentage here. It's something roughly about like 5%. I'll be able to meet 5% of the data. So this is how the variability is normally comes into play to answer this sort of a question. So what it means is basically from the center across the standard deviations, there is a certain amount of certain percentage of the data that you can relate to. So you can say that, hey, from the center, with the variance of 1 standard deviations on both sides, minus, that is from -1 standard deviation to +1 standard deviation, I have roughly 68% of data, which is 19 plus 19, 34, and 38, and 50 plus 15 plus 50, 30. So that would be 68% of the data. So and likewise, but here we are trying to target only the upper limit. So we only need the upper limit, we are not requiring the lower limit. So we'll only focus on the upper limit, not on the both sides. So what I'll do is I'll just go across my x-axis and see where is my 80% mark reach is met with. So I'll go on my cumulative percentage line. So 70%, 80%, and 84%. On a +1 standard deviation segment, I will reach about like 84% of my customers. So but since my target is only 80%, I can go about like something, say 0.7 or 0.8 standard deviations. So what should I, how much should I set the value is, you take a mean and calculate the mean, and to that mean add just 0.8 of the standard deviation, and that should be your limit that you should set to reach at least 80% of your customers. So this is how a typical normally standard deviation or variance can be used. This is again one of the basic examples. There are innumerable ways you can actually use this. This is just one of those examples. Okay, so that is how you create a upper limit. Now, often cases where it's not just the upper limit that you want to set up, but you'll also want to set up a lower limit. Okay, think of, let's just go to a second example. Okay, think that you are a manufacturing company and you are producing, let's say, these scientific calculators. Okay, and every calculator, let's say you're producing some n number of calculators per day, and it happens that not all the calculators that you produce are perfect. Okay, there might be one or two pieces which are defected and cannot be used. It happens that normally that happens, and now you need to let's say if this number of defected pieces that you're producing per day, if it increases, that obviously will create some sort of dissatisfaction in the customers who are using your calculator. So you need to keep that number of defected pieces to a limit. So there should be an upper limit on that. It should not cross beyond that. Let's say tolerance, it cannot exceed 10 pieces per 1 lakh pieces that I produce. Okay, if I produce 1 lakh, the number of defected pieces should not exceed more than 10. So that is an upper limit. But you can pull up a similar sort of analysis that we did for our milk consumption. But there could also be a lower limit on the calculator production manufacturing case. So think of it as something like this. Okay, for you, in order to make every calculator defectless, okay, it involves, or from your side you have to make a certain decisions or incorporate certain what we say check processes. Okay, you have to involve some certain processes which make the entire production, let's say, less efficient or slow. So what happens is, let's say the upper limit is 10, right? So if instead of that 10, let's say, hey, if I produce 1 lakh units, I don't want any defected pieces, I want that to be 0. So for that, you need to have a production line which is very perfect. Okay, which doesn't possibly, so that involves that, hey, you may have to put in a lot more manual checkups or a few more additional steps, which only consumes more time and which also might reduce your manufacturing capacity. So that may not lead to you generating enough sales to run the company. So that is on the lower side. So there is a upper threshold in terms of customer satisfaction and the lower threshold in terms of viability of the business being run, right? So in this sort of a situation, you have both the limits. So you need to make sure that your number of defected pieces will not cross the upper limit, because if it will cross, it will cause customer dissatisfaction. But at the same time, there is a lower limit. Even though we would like that, hey, a number of detections to be 0, but I cannot target that to 0, because if I have to target that to 0, it will just increase the production time and all the costs, etc., for me to make sure that nothing is going wrong, and that becomes not so viable for the business. So there's a lower limit as well. So you should let's say in the upper limit we have set up as 10, lower limit let's call it as 3. So below 3, it's not feasible for our business. So this is how we can normally set up a upper and lower limit beyond our mean and try and in the entire duration of the manufacturing process, you can see, hey, your number of defected pieces for every batch of 1 lakh calculators is always in between this 10 and 3. And that sort of analysis is something called statistical control analysis, and that can be monitored using something called that, which we are all familiar with, statistical control chart. This is also very much about the same. We have the middle line that we see there is the mean, and think of all the dot and the red lines above and below that green line. You can consider them as upper limit and lower limit, and the dotted line is actually, you can consider related to our example and say how many defected pieces or something similar to that. So wherever it crosses the limits either above or below, you can consider them as something is going wrong, and you have to take an action to bring it in between the limits again. And yeah, so this is statistical control analysis, and statistical control chart is something little more, a lot more than what we have just seen, but I think this should be a broad a brief about the same. So control chart indicates whether a process is in control or not. So they try to monitor all the manufacturing process or wherever it is applicable, and use a control chart to monitor the same. It determines the process variability and detects the unusual variations taking place in the process. So all the points in the red are noted as unusual variations, the variations that which are not desired. Okay. And UCL is normally termed as upper control limit and lower control limit. So yeah, so that's on the that is how normally the measures of variabilities are used in a statistical. Just to give a few examples. Now let's see what are the different types of measures of variabilities are available. Okay, so first one basic measure of variability is the it's something called deviations, and it's calculated as the difference between the observed values and the estimate of location. Estimate of location means measure of center. Let's say it's similar to an error. So these are the other names that we call deviation. So if you have a set of values, you just take the mean of that value and calculate the difference of each of those value from the mean. So that is what it's termed as deviations. So our errors, we normally in our frequent terms we call it. And there's a next measure of variability called variance. Okay, once you have your deviations or errors, they're calculated. It's just the square those errors whatever you got, and take a sum of all those squared deviations, and divide that by n-1. So if you have n data points, you need to divide that sum of square deviations by n-1 to get the variance. Why we have to divide by n-1? It's a separate, it's a slightly different topic. We'll not get there. It involves something called concept called degrees of freedom. We'll try and see if we can cover it in some of our future sessions, but for the time being, let's just take it as if there are n points in a sample, then we need to divide the sum of square deviations by n-1 to get the variance. And in other words, this variance is also called as mean squared error. Error is deviations and mean squared error is variance. And once you have this variance, standard deviation is nothing but the square root of the variance. If you see almost all of these three are related, it's just the this is what the standard deviation is. And standard deviation, since it's a square root of the variance, okay, it will always be positive. Okay, think of it as here the deviation can only be it can be both positive and negative. Your value can be above or below mean, but think of standard deviation as an absolute magnitude of mean of absolute magnitudes of all these deviations. So that's what this particular standard deviation means. And these are the other norms that other names that which we may call standard deviation by. We call something called L2 norm or Euclidean norm. Yeah, but we'll try and use standard deviation. There is something called mean absolute deviation. So this is something that is very similar to standard deviation, but it's very it's calculated in just a different way. Okay, for example, we just saw that standard deviation is nothing but mean of absolute deviations, right? It means that, but it's not actually calculated like that. But whereas the mean of absolute deviation here, this metric is actually calculated in that sense. So what they do is they get all those deviations, and if it's plus 5 or minus 5, they take absolute value that will be 5 for both the plus 5 and minus 5, and they get those absolute deviations and take a mean of that. So that is the mean absolute deviations. So this is supposedly a similar metric as standard deviation. It shouldn't be, if you have, say, let's say perfect normal distribution, most likely that this mean absolute deviation and standard deviation will both coincide. So but whenever you have outliers, this mean standard deviation might tend to standard deviation and mean absolute deviation, they tend to vary a little. And the logic between these two is that just like how we have between mean and median, whenever we have outliers we need to use median, and whenever we are not having outliers we can go with mean, right? So similarly, if we have outliers in the data, it is recommended that you go with the mean absolute deviation. Okay, it's important that the calculation methods are different for both of these, standard deviation and mean absolute deviation. But if you observe that, hey, there are no outliers, you can go for the standard deviation. So, and next we have something called range. I don't have to explain, which is something that you already are familiar with. It's basically the difference between the maximum and the minimum value in the set of values that you have. And percentile, I'm pretty sure that you're familiar with this as well. Quantile, it's the other name that which we call. So so it's basically says that, hey, what is the value in the set of values that I have, so that X percentage of my data points lie below that. So if you see the question that which we answered here is something similar to percentile. So what we are trying to get here is, hey, tell me the data point on x-axis where my percentile is 80. So that means 80% of the data lies below that. Let's say, for example, we have seen in the 80% lies about some 1 point plus mean 0.7 or 0.8 standard deviation. So let's assume that is the value of 13. So it roughly with the 80 percentile is something in this data set is something like 13, right? So so 13 will hold the value of 80 percentile, and as you progress across the 20 or something 19 will have some 98 or 99 percentile, some that sort of data. Most of the data lies below that. So that is a percentile. And there is something called interquartile range. Okay, and this is something that is related to percentile. It's just the difference. You calculate the 75th percentile, just like how we calculated the 80 percentile in the milk consumption example. You calculate 75th percentile, what is the value, 25th percentile, what is the value, and take the difference between both these values. So that is normally termed as interquartile range. So these are the few normally frequently used or popularly known measures of variability. And let's try and see a little bit more on interquartile range. That is something can be a useful measure as well. So if we see here on the top, I have a typical distribution. Okay, it's not a perfect normal distribution. I can see some outliers. I can see that it is skewed, right? I have that, and below that I have, for the same distribution, I have a box plot, box and whisker plot. So we can see, you can understand that normally Okay, let's just go one by one. So in the box and whisker plot, normally it is used when you want to show a little bit more information about a distribution. So if you see the top histogram, it's not showing any information. At max, you can show mean or standard deviation, but the box and whisker plot show a lot more information as well. So for example, the center line that we see here, right, it's corresponding to the median. It should correspond to the median of the distribution. So what does that mean is, below this line there is 50% of data, above this line there is 50% of the data. So that is the median. So if it is the case of standard perfect normal distribution, then all your mean and median will coincide on the same line. So but it is not here. So we have a median here, and there are few more lines here. We have something called Q1 and Q3, right? So these are the 75th and the 25th percentile data that which we saw. So if you see under Q1, I have only 25% of the data, so it's called 25th percentile, and under Q3 I have 325s, which makes 75. So the difference between this value and this value is called as IQR, interquartile range. And I have something called lower whisker limit and upper whisker limit. Let's see how to calculate this and what is the importance of this in a moment. So it's same. Upper whisker limit is normally calculated with whatever the 75th percentile is there, plus you give a 1.5 times of IQR, whatever the range you have found here. You add 150% of that to Q3 to get the upper whisker limit, this value, and you remove 150 or 1.5 times of IQR from the Q1 to get the lower whisker limit. And this upper whisker limit and lower whisker limit, I think Jairam asked in the previous session that if there is any way that we can quantifiably, rather than just eyeballing the distribution, if we can identify all the outliers, right? So this would be the proper method to come identify outliers, quantify in a quantified manner. So everything that falls above this upper whisker limit or below this lower whisker limit, you can term that as outliers. As you can see, there are two data points here. So as we just saw, that box and whisker plot holds a lot more information than the typical curve-based distribution that we are used to see up until now. So normally people, whenever they want to show distributions, they prefer box and whisker plot. So they get all these outliers and these different quartile ranges and the limits as well. Only thing that they will miss in the box and whisker plot is that the nature of the distribution. Was it so they won't be able to understand the nature of was it a perfect bell-shaped, or was it any skewed? If at all it is skewed, like how much skewed it is. So that information they will only be able to eyeball it from the histogram, but not from the box and whisker plot. But apart from that, this holds a lot of information as well, other information. So you can consider this as a very good alternative to display the distributions. I think we are actually out of time, guys. I just wanted to stop here, and we'll continue with this. We'll see some of the examples in Excel in one of our next sessions. But I just wanted to open up for any questions at the moment. Okay, I think that's it.